Hi there, welcome to this lecture series on matrix algebra. This is part 2 of lecture number 4. The topic is special matrices. And in the second half, we'll continue looking at special types of matrices, identity matrices, etc., and their properties. Okay, so let's continue. Let's first introduce a concept called inner product. It's defined as the follows. Given two column vectors of the same length, let's call one of them x with length n, and the other is y, also with length n. So the elements will be xi's and yi's. Then the inner product is defined as a product in this specific way. It is the product of x transpose with y. So since x is a column vector, then the x transpose will be a row vector, and then y is a column vector. And you perform this multiplication, and what you get is a matrix of 1 by 1, meaning you just get one number, and it will be the element-wise multiplication of each element. So x1 with y1, x2 with y2, all the way xn with yn multiplied, and then you add up all these products. Okay, so since this is just a 1 by 1 matrix, and it is often identified as a number. Now let's review the concept of the numbers 0 and 1. For real numbers, these are two special numbers, and they have the following special properties. So if, let's say, pick an x, any x, that's a real number, and then we have the following. X plus 0 is x, meaning adding 0 on top of x does not change it. And the other one is x times 1 is x. So multiply x with the number 1, it does not change it. So the following question would be, are there matrices with similar properties? So let's look at the zero matrix. What is a zero matrix? Let's say a zero matrix of size m by n. This is a matrix of size m by n where all the entries are 0, just a block of all 0 in this rectangular shape. So you see all the column vectors are 0 vectors and all the row vectors are 0 vectors. And then we can easily verify the property of a 0, meaning that if you have a matrix of the same size, m by n, and then you add up A with this 0 matrix, and you can easily see that you get A back, so it doesn't change the A matrix. Next, let's look at the identity matrix, which is the equivalent of the number 1 for real numbers. So this one is defined actually for a square matrix. So n by n identity matrix, we'll denote it by capital I and with a under subscript n to denote the dimension. This will be a matrix that is 1, all the elements on the diagonal is 1, and then everywhere else it's 0. Okay, so we can denote the element at position jk by this symbol delta. It's kind of a delta function. There's a thing called delta function. Delta of jk, where delta of jk has the following property. If j equals k, then it's 1. Otherwise, if j is different from k, then it's 0. So you see when j equals k, and this denotes exactly a diagonal element. And all the others, when j is not equal to k, the element will be off diagonal. So let's verify its property in the multiplication. Let's consider an A matrix, which is m by n, and we will try to multiply it by an identity matrix. And then we need to specify if we multiply it on the left or on the right, because it matters, because the size will have to match. Okay, so if you multiply it on the left, then you have to put a identity matrix of size m times m. And we wanted to recover the A matrix. And similarly, on the right, if we multiply with the identity matrix of size n, m by n, and we want to recover the A matrix as well. And one can easily carry out a definition proof, kind of check the definition of the product, and you see that these two properties, they hold. Okay, one can take a simple example for some small matrix A. Let's say it's 2 by 3. It has the elements ABC, first row, DEF, the second row. Okay, let's multiply on the left by a 2 by 2 identity matrix, which is 1, 1 on the diagonal and 0, 0 otherwise. And we carry out this product. Okay, so what is the result? Well, so you can do the first row in the product, the first column, that you get A. First row, second column, you got B. First row, third column, you get C. And then second row, first column, you get D, and so on and so forth. And you see that this is exactly the A matrix. Let's check the multiplication on the right. So we're going to perform A times identity matrix 3 by 3, which is this matrix here with 1 on the 3 diagonals and zeros otherwise. Okay, and it's not difficult to carry out this computation. You can take the first row and cross the first column, then you pick up the A because that's 1. And then the first row with the second column, you only get the second element, which is B. And the first row and the third column, you get the third element here, C. So you get ABC as the first row. And then for the second DEF, it's the same. You take this one cross that, you get D. And you take this one cross that, you get E. And you take this cross that, and you get the F. And we recover the A matrix. Okay, so let's do a quick proof to show that A times IN on the right equals A by definition. Okay, write it out and see that this is true. Okay, so let's take the A matrix and we write the elements of it to be A, I, J, and this is a M by N matrix. And then we want to multiply it on the right by an identity matrix IN. And the IN will have element delta JK for the jth row and the kth column. And the delta JK has the property that if J equals K, it's 1. If J doesn't equal to K, it's 0. Okay? And then let's say A times IN, let's call this result to be vector C, the product of it, and let's denote the element to be IK. And then we know the element in C is computed by summing up this product in this specific form. So we'll be summing up the product Aij times delta jk, and j goes from 1 to n. then it's convenient here maybe to write out every term. So I will have ai 1 when j equals to 1. I write this out. And then here is when j equals 2. And then here I pick a term. That's the term when j is equal k. So aik delta kk. And so on and so forth, and until the last one when j is n. So we see that we have n terms that we are summing up, and we're going through this delta with the second index k and the first index going from 1 to n. Then there is only one term here of this delta where the index will be exactly k. Okay, so because the first index is going from 1 to n, then somewhere it will be k and matches the second index. And there will be only one term which we mark as red because that's a special term. Because for delta, if the two indexes are the same when j equals k, it's 1. So this delta is 1, and all the other deltas in blue will be 0. So all these terms, there is only one potentially non-zero term. One non-zero term for delta, all the others are 0. So this delta is 1 here. I have only this term. Let's put in delta as 1. Then I exactly get aik. And that argument is valid for any index I or k. And therefore, the A matrix is the same as the C matrix because all the elements are the same. Okay, and let's look at a couple of special matrices, more special matrices. The next one is called a diagonal matrix, and this is only defined for square matrices. So A now is a matrix of size m by n, and its element is called aij, that we denote like that. And this is called diagonal if all the elements outside the main diagonal are 0. So in particular, this means aij, all the indexes will be 0 if it's not on the diagonal. That means if I does not equal j. Okay. So an example will be a matrix like this. All of these on the diagonal potentially can be non-zero, but everything outside will be 0. Next is a square matrix m by n, is called an upper triangular matrix if the following is true. That is, all the elements below the main diagonal are 0. This means aij will be 0 if it's under the main diagonal, which means the index I shall be bigger than j. So recall, I is the index for the row and j is the index for the column. If I is bigger than j, and then it's below the main diagonal. So we can, for example, write this out. So this is the main diagonal, and below it's all 0, and above potentially not 0. We don't put restriction on that. And the name upper triangular is given due to the shape of the non-zero element here. It is the upper half of this is like a triangular. Okay, let's take an example. We are given now 3 matrices A, B, and C. We want to know if any of them are diagonal, any of them are upper triangular. Okay, so let's look at A. Is A diagonal? Well, yes, it is, because it only has non-zero element along the diagonal line. So it is diagonal. And then is it upper triangular? Well, let's look at everything below the triangle. Down here, it's all 0. Yes, so it is also upper triangular. Well, actually, with this discussion, we are making an observation that any diagonal matrix is also upper triangular because it's always 0 here under the diagonal line. Okay. Now let's look at B. Is B diagonal? No, because you have non-zero element outside the diagonal line. Is B upper triangular? Well, let's look at under the diagonal. It's all 0. So yes, it's upper triangular. And so that's for B. And now we have a C matrix. So this is like a trickster. So remember, the diagonal line is defined as this line going down. So C here has non-zero along this line, but be careful, this is not the diagonal line. The diagonal line is the line that goes downward. Okay, so because of it picked the wrong line to put non-zero element, therefore it's neither diagonal nor triangular. So is it triangular? So let's look at under the diagonal. This part, is it all 0? And no, we have the 9 here. Okay, so it's not upper triangular either. Okay, and there is another concept called a tridiagonal matrix A. So a matrix A here, it's a square matrix n by n. It's called tridiagonal if all the elements A, I, J are 0, if their indices difference between I and J is strictly bigger than 1. Okay, let's look at a matrix. Let's say the matrix written like this. So along the diagonal line, we know that I equals J. So I minus J is 0 along the diagonal line. And then this one, let's call this upper diagonal because it's right above the diagonal line and it goes in the same direction as the diagonal line. Let's look at the index. It's 1, 2, 2, 3, 3, 4. So the difference between the two indices I and J is I minus J is negative 1. And the absolute value of I minus J there is 1. Okay. And then let's look at the lower diagonal line, the line that's below the diagonal, and then we'll have indices 2, 1, 3, 2, 4, 3. And the difference between I, J is 1. Okay. And then all the others further out, the difference I minus J will be bigger than equal to 2. So they will all be 0. So now you see why we call it this name, tridiagonal. So there will be 3 lines, one on the diagonal, one is upper diagonal, one is lower diagonal. Along those 3 lines, you can have non-zero element. And everywhere else, all the elements are 0. So diagonal and tridiagonal matrices are of interest for many of the nice properties they have. In particular, they are very easy to solve. They can be solved very efficiently with a very quick algorithm. We'll come to that later. Okay, so one last concept of a special matrix is called a sparse matrix. A sparse matrix is particularly useful when you have a huge system. Let's say A is a matrix of 1 million times 1 million. And then when the memory space of storing this matrix becomes critical and also any computation will take a long time, then if in particular this matrix is called sparse, that is, most of its entries are 0. There are a very small percentage of the entries that are non-zero. Then this is called a sparse matrix. Okay, and then you can design special algorithms using this property to do the matrix calculation. Okay, and you have noticed maybe that we just covered 2 sparse matrices, the diagonal matrix and the tridiagonal matrix. They are all sparse in the sense that the non-zeros are only on the diagonal or on the tridiagonal line, and everywhere else the matrix is 0. Okay, so that's a very sparse matrix. Okay, so that's all we will cover in this lecture, and we'll continue our study on matrices in the next one. And I hope you enjoyed this lecture. I'll see you next time.